In this lesson, we're going to be talking about turning points of a polynomial. A turning point occurs whenever the graph of a polynomial function changes from increasing to decreasing or decreasing to increasing. Turning points are associated with local maxima or local minima on a graph. The graph to the right has turning points at x equals -2 and x equals +2. So if we look at this graph a little bit more in detail, increasing, you're looking at what happens starting at the left, just like when you read a book, you start at the left. And so if I'm traveling on this graph, here it's going to increase, it's going to stop at that maximum point, it's going to decrease in this interval, then I've got a low point, you're just sitting in a ditch down there, nowhere to go, and then you have an increasing interval. So again, it increases, it stops, it decreases, and then it increases again. So by definition there, it's saying that a local maxima or local minima, so a maximum and a minimum, occur at those turning points where it changes from increasing to decreasing intervals. So this guy, again, we would refer to as a maximum. This one we would refer to as a minimum. Again, it's king of the mountain or you're in a valley. Now, the next thing we're going to talk about is the number of turning points. So it says a polynomial function has a degree n. The maximum number of turning points is n minus 1. So we're going to be asked to graph the problems 1 and 2. And I'm going to start by finding the degree. It is not listed in our steps, but I think that's really important. So in the previous video, we talked about looking at the exponents. If you were to take this binomial and multiply it out, you would end up with an x squared term. And if I were to take this binomial, it has no exponent, which means the exponent is 1. So this would be x to the first. And adding those exponents means that the degree of this polynomial is going to be 3. So my degree is going to equal 3. Now, using this new information, if the degree is 3, the maximum number of turning points is going to be n minus 1, or in this case, 3 minus 1. So before we even graph, all I know is it's going to have at most 2 turning points. All right. Let's go from there. Find the real zeros and the y-intercept of the function. Well, the real zeros are also referred to as the x-intercept. So we're kind of doing these two steps at the same time. To find the x-intercept, you plug 0 in for y. So my p of x represents my y there. So I'm going to have 0 is equal to x minus 1 quantity squared times x minus 3. If I were to set each one of those equal to 0, this binomial equal to 0 would give me a 1. And this binomial, if you set it equal to 0, would give me x equals 3. So that's telling me that my x-intercepts, first one is going to be 1, 0. The second one is going to be 3, 0. Then it asks me to find the y-intercept. Well, to find the y-intercept, you plug 0 in for x. So if I go through that, plugging 0 in for x, I'm going to keep that p of x. In this case, I'm going to write it as a y. Plugging zeros in for my x, I have 0 minus 1 squared and 0 minus 3. So negative 1 squared would be a positive 1, and 0 minus a negative 3, that's going to give me a negative 3. So 1 times negative 3 is going to give me a negative 3. So that means that my y-intercept now, give myself some space, my y-intercept is going to be at 0, negative 3. So again, y-intercept, the number's in the y spot, x-intercept, the number's in the x spot. So let's go through and plot these points. So I'm going to have a point at 1, 0 and a point at 3, 0. And again, those represent my x-intercepts and also my zeros. Those numbers or words are interchangeable. My y-intercept is going to be down here at 0, negative 3. Now, I can also just kind of visualize how this problem is going to look because I know when it's a degree of 3, 3 is odd. The leading coefficient here is not listed, which means it's going to be positive. So if it's an odd degree with a positive coefficient, that means it's going to look like a line. So that means we know it's going to start in that bottom left-hand corner. Not sure what it's going to look like in the middle, but it's going to end up in that upper right-hand corner. Okay, so from there, now I'm at step 4. Plot the points from your table. Oops, step 3. Make a table for several x values that lie between the real zeros. So again, you're asked to graph. A graph is supposed to be specific. A sketch is kind of lazy. You're focusing on those key characteristics. So if we want this to be a little bit more clear, we have our, let's say this is just my XY chart. I can choose any numbers that I want, but to the left of my 1 here, I already have a point at 0, -3. Again, that was called my y-intercept. I could put this here if we prefer. So I'm going to look now between 1 and 3. So let's say I test 2. I'm going to find a y value that corresponds with that. And then I'm going to look at something to the right. It doesn't make a difference. Let's say we choose 5. Because why not? So I'm going to plug these numbers in. If I plug 2 into this function, I'm going to have 2 minus 1, which is 1. 1 squared, which is going to give me a 1. And then same thing 2 here. 2 minus 3 is going to give me a -1. So that's going to be a -1. So if I multiply those together, I get a -1. So one additional point on my graph is going to be 2, -1. Let's repeat this process for the 5. If I plug this in, 5 minus 1 is going to give me 4, and 4 squared is 16. 5 minus 3 is 2. Ooh, that's going to be pretty big. 16 times 2 is 32, so my second point is going to be 5, 32. So let's put those on our graph as well. So I have 3 accurate points currently. Let's plot these remaining 2. So I've got a point at 2, -1. And then my next one is supposed to be at 5, 32. Holy cow, that's super high. So basically I know when it's intersecting or I'm looking at 5 right here, it's going to be shooting up way off my coordinate plane. So let's just pretend it's like up here. Just for sake of conversation, let's just pretend this is 32. Okay, so we're ready to draw this graph. I'm going to start in the lower left-hand corner in quadrant 3, just like we were talking about with our line. And I'm going to draw it so that it intersects or touches all of these points that we plotted on our coordinate plane. So it's going to start here as I get close to the 1. Well, it can't go through. That's kind of crazy because if it goes through, it's not going to pick up that 2, -1 point. So let's erase that. If I look back at the beginning, where did I get the 1? Well, I actually got that 1 point from this binomial. And if we refer to that and we look at that as being an x squared, that means it needs to look quadratic at 1. So as I draw this, it's actually going to bounce off this 1, 0. So it's going to look parabolic. It's going to pass down to pick up the 2 as it heads back up to that 3, 0. Let's look at the degree there. This degree was 1, so it means it's going to look linear at that point. So it's going to pass through. And I know it's supposed to go way up here to 532. Again, way, way, way off my grid, but something like that. So again, it's starting in the 3rd quadrant. It's going to bounce off this 1, and it's going to pass through the others. Let's look at a second example. Now, in the previous problem, the first thing we did was look at the degree. It was not one of our steps, but it did help us to graph the polynomial. So if we look at this problem, this first binomial is to the second. And again, if you were to multiply that out, that means that there would be an x squared. The second binomial, this guy, also has a square there. So if you were to multiply that out, that would also be an x squared. So that means that the degree of this polynomial, if we add those exponents, is going to be 4. The leading coefficient here is positive, so I have a positive even polynomial, which means when I do graph this, it is going to look similar to a quadratic. It's going to start up, no idea, and it's going to end up. All right, so let's get a little bit more serious here. Find the real zeros and the y-intercept. Well, the real zeros, again, those are the x-intercept. Those terms are interchangeable. So if you're going to find the zeros or the x-intercepts, your job is to think about what happens when I plug 0 in for y. So if I replace that y with 0, this 1/12 here is going to change the size of my polynomial a little bit. But my job is to solve this. I'm going to use my zero product property, which means I would set each one of these terms equal to 0. So if I set each term equal to 0, the 0 equals 1/12. That's a contradiction. But if I set 0 equal to x plus 2 quantity squared, that's going to give me an x-intercept or a 0 at -2. So again, I'm calling this an x-intercept. It is a 0 as well, so I'm going to have one at -2, 0. And if I set this binomial equal to 0 and solve, I'm going to get a +3, 0. So those are going to be 2 points on my graph. All right, let's look at the y-intercept. When you do the y-intercept, you're plugging zeros in for x. So if I plug zeros in for x, I'm going to have 0 plus 2. So 0 plus 2 squared, which is going to give me a 2 squared. 0 minus 3 is -3, so I'm going to have a -3 squared. If we keep going, multiply that out. I have 2 times 2, which is a 4. I have -3 times -3, which is a +9. This is going to give me 36 divided by 12, which is going to be 3. So that means that my y-intercept here is going to be 0, 3. Let's plot those points. So I have an x-intercept or a 0 at -2. I have an x-intercept or a 0 at 3. And I have a y-intercept at +3. Now, to get a little bit more accurate, let's find some additional values. So making a table, leave myself very much space. I'm going to look for a point on each side of this 0. So here, let's say I plug in -3, see what y we get from that. Let's say I plug in, I don't know, -1, see what happens there. Let's say I plug in +1, and let's say I plug in, I don't know, +4. Let's see what happens with those values. Okay, so now when I plug -3 in, I ended up getting a +3. I did this on a separate sheet of paper already. When I plugged -1 in, I got 4/3, or 1.3. 3, I should say. When I plugged a +1 in, I got a +3 again. Well, that's interesting. And when I plugged a +4 in, that gave me 3. All right, let's plot those points as well. All right, -3, 3 is going to put me here. And -1, 1 1/3 is going to be about here. 1 +3 is going to be back up here. And then I'm at 4, 3. Wow, that's crazy. Well, let's connect these points. Well, I know the degree was 4, so it's going to look parabolic. We said that up here, which means it's going to start up and end up. Leading coefficient's positive. And let's connect those points. So it's going to start in the second quadrant. It's going to start up here. It's going to pick up that 3, 3 point. And as it heads down here, let's look at our equation. I got the -2 from this. It was raised to the second, which means it's going to be quadratic. So it's actually going to bounce off of that -2. It's going to pick up the y-intercept. It's going to come back down. As it heads back to the 3, this was x minus 3, raised to the second as well. So that means it's going to look quadratic. It's going to bounce back off that one and pick up this point. All right, we actually started with 2 of the more challenging problems. 3 should be easy peasy for you. Use the graph of the polynomial function shown below. How many turning points and x-intercepts are there? Is the leading coefficient positive or negative? Is the degree even or odd? What is the degree? Okay, how many turning points and x-intercepts are there? So when you're looking at turning points, again, you're looking at changes in direction. So when I trace this, starting again in the upper left-hand corner, this decreases, it increases, it decreases, it increases, and it decreases. So when you're looking for turning points, you're looking for changes in direction, which means I have this guy here. This is going to be a turning point. It increased and decreased. This is another turning point, and then again, increased and decreased. So I had 3 turning points in my graph. Erase that just to clean it up a little bit. All right, so I had 3 turning points. All right, let's look at the x-intercepts, which again are referred to as zeros. I have an x-intercept here, I have an x-intercept here, and I have an x-intercept here. So one x-intercept is at -1, so we're going to write that as -1, 3, or sorry, -1, 0. Another x-intercept was at 0, so that's the origin, 0, 0. And my third one was at 2, so that's going to be 2, 0. All right, is the leading coefficient positive or negative? Well, the first thing I'm noticing here is it is odd. I know that's not asked in a specific order here, but I know it's going to be odd because if it's even, whether that means it's going to be x to the second, x to the fourth, x to the sixth, they're all going to look quadratic in form. So that means it's either going to start up, again, not quite sure, but it's going to end up, that would be if there's a positive leading coefficient, or it's going to start down and end down if it was a negative leading coefficient. Well, that's not the case here. This point, or this spot, the arrow is going to be increasing forever and ever in the positive direction. This is the opposite. It's decreasing. So it's an odd function because they're not headed in that same direction. So what is the leading coefficient? Well, if you think about this, if this is odd, maybe it's an x to the first, maybe it's an x to the third, an x to the fifth. They're still all going to look linear in terms of those endpoints or that end behavior. So if this one is starting at the upper left and it's ending down at the lower right, it's going to look something like this. Again, it's going to get a little bit more exciting in here. This is pretty boring, but it's going to start in the upper left-hand corner and end in the lower right, which means it is decreasing. So it's going to have a negative leading coefficient. Okay, what's the degree? This is when it gets exciting. So if we look at the degree, it's going to bounce off at -1. So it looks quadratic at this point. Now, I'm going to say the degree there is 2. It could be higher. It could be 4 or 6 or 8. But if I'm writing it with the least degree, that would be 2. If I look at what happens at this 0, it passes straight through like a line. So at minimum, it's going to be a degree of 1. It might be another odd. Going back to my last 0 at 2, it's bouncing off this one or looking like a quadratic. So I'm going to call that a squared. So for the degree, the total degree I'm looking at, if you add all those together, is 5. So this is going to be a 5th degree polynomial. Now, like I said, even though this looks quadratic, it might be a larger exponent, and we're going to explore those as we keep going. Okay, for the last one, you're going to need a graphing calculator, and this is going to take you a little bit of time. So it says accurately graph each polynomial. I'm just going to give you one to try. You can try others on your own. Use your calculator to find the exact minimum and maximum values. Then use your graph to state all of its characteristics. Well, we need to be as specific as we can with our points, but I'm actually going to see if I can answer some questions before I even substitute or plug this into my calculator. Okay, let's look at the degree. Well, the degree is always the highest exponent. So if I'm looking at this problem, my degree is going to be 3. I know it's going to be odd, well, because 3 is an odd number. Interesting. All right, and so if we think about an odd function or an odd polynomial, if the leading coefficient is positive, it's going to end up looking similar to a line, which means it's going to start in the lower left-hand corner. Not quite sure what it's going to do in the middle. Might be something fun. It's going to end up in the upper right-hand quadrant. So starting in that third quadrant somewhere, ending up in that first quadrant. Again, real fuzzy what's happening here. So that's where the exciting part comes in. All right, so I know it's going to look something like this. How many possible turning points? Well, that's interesting. We talked about on the slide previously that there is always going to be n minus 1 turning points. So in this case, n was 3. So n minus 1 means that there's possibly going to be 2 turning points. We're going to keep that in mind when we graph it. All right, well, let's get started. Now, in previous problems, these were given in factored form. This is not given in factored form. It's a standard form. So we're going to start by substituting that into our calculator. So take a second to do that now. All right, I've got my graph on my calculator. I'm not going to ruin it by telling you what it looks like, but I can see my end behavior, and I can actually have identified that at this point. Because I know if it's a positive, it's a cubic, correct? It has the largest exponent is x cubed. It is going to be increasing starting in that third quadrant. And whatever it looks like in the middle, not sure yet, but it's going to be heading up forever in that right direction, in that first quadrant. So if we're looking at our end behavior, as x heads to positive infinity, the y is also going to head towards positive infinity. So even though I don't have an accurate graph, I'm focusing on this sketch down here. In terms of the end behavior the other direction, as x heads to negative infinity, then the y is going to be heading to negative infinity. Okay, let's get a little bit more specific. Now, there's a couple different ways you could do this. If you go to your table, that is second graph, so if you push second graph, right above that it says table. And we're going to choose some nice accurate points from our table. So what does it give me? It tells me that I have -1, -7. So let's check that one out. -1, -7. It's going to be here. 1, 2, 3, 4, 5, 6, 7. Yep. It also gives me a point at 0, 2. So that's going to be here. It gives me another nice point at 1, 1. And I'm really just stealing these out of my table. 2, -4 is going to be down 1, 2, 3, 4. 3, -7. Wow, it's giving me some nice points. I'm actually going to switch my color here. These are kind of tough to see. So I've got 1 here. I have this guy. Ooh, that's my y-intercept. That's pretty neat. I have 1 at 1, 1. I have 1 at 2, negative, what was that? 2, -4. I have 1 at 3, -7. So over 3 down 7 would be about here again. And, ooh, 4, -2. 1, 2, 3, 4. And it's just going to keep on going. At some point, oh, there you go. 5, 17. That's way, way off my graph. Before I connect these points, I'm going to look at my graph on my calculator one more time. And I'm going to actually go to that calc screen. C-A-L-C. It is right above the trace. So you're going to push second trace. And when you look at that screen, you're going to see some key words. 0 is one of the words. That's number 2. And 0 again, those are my x-intercepts. So I'm going to be looking at those. Number 3, it's minimum. So we're going to use that to help me find my minimum values. And number 4 is max. So we're actually going to go through and try all of those characteristics. So let's start at 0. If I arrow down or push 2, it's going to give me something that says left bound and right bound. So you're going to move the cursor a little bit below that x-intercept. Not sure where it is again. Push enter. You're going to push the right arrow, which is going to go a little bit above. You push enter again, and then it says guess. Well, guess just means move that cursor as close as you can to that x-intercept, and it comes out. It's not very pretty. However, I'm going to use, let's say, 2 decimal points for that. I'm going to round to the hundredths. It is negative 0.39. So this first zero is negative 0.39. Now, you can write it as an ordered pair. You don't have to. I don't have that much space. So let's just write it as an x value. Negative 0.39. So on my graph now, negative 0.39 is going to be about here. Well, I see 2 other zeros or x-intercepts on my sketch. So I'm going to repeat that process. I'm going to push second trace. I'm trying to find the zeros, so I'm going to push that 2 key. It says left bound, so I'm going to push that right arrow. So I'm just a bit above that x-intercept. Push enter. I'm going to keep going to the right. Push enter again. Now it's a little bit below the x-axis. And arrow again to the left. It says guess. If I push enter, it says 1.2271344. That would be my x. My y is 0. So let's round it again to the hundredths. So my second zero is going to be 1.23. 1.23. So that'd be about here. All right. Again, looking at my graph, I see one more. Let's do the same thing. Second trace. 2 for the 0. Arrowing to the right. Left bound, I'm going to push enter right below that x-axis. I'm going to arrow further, push enter right above. Guess, moving as close to that x-axis as I can. And this time it says 4.16. So I'm going to go over here at 1, 2, 3, 4. 1, 2, 3, 4.16, about there. All right, well, I think I'm good to go, but it did ask me for some other values, relative max, relative min. And since I mentioned that down here, let's walk through the max and the min. So same strategy when you're trying to find those variables or those values. You're going to push second trace. Let's say I find the max first. That's what it's asking me for. I'm going to arrow down to 4 or push 4 and press enter. Now, the max is the high point. And we talked about before, there's going to be 2 turning points, because if the degree is 3, it's 3 minus 1. So when I look at my graph, I see a maximum, and it says left bound. Same thing. I'm going to use my left arrow. I'm going to arrow over, so it's to the left of that max. Push enter. Right bound, I'm going to arrow over. Push enter again. Once it's past that hump, guess means I'm going to put it as close as I can. And this time it's telling me my maximum value is at 0.33. And the y is at 2.48. So 0.33, 2.48. 0.33, 2.48. So that's going to be about here. All right, so I can already see what's happening on the left. You can kind of get an idea if you're connecting those points. Relative min, I see one in the 4th quadrant. Same process. Second trace. Again, now we're at our min. This is our min. So you're going to push 3 or arrow down and push enter. Left bound. So you go to the left of that low point, that minimum. I'm going to push enter. Right bound. I arrow past it. I push enter again. Guess, move that cursor as close as you can and push enter. And so what I got for that is 2.999. I'm actually going to round that to 3 since that 9 keeps repeating. So 3, -7. Now, 3, -7. Oh, look, I already had that value before. So let's connect these dots here. Too excited about this one. I don't want to wait anymore. So if I start down here in this, again, I'm down here in quadrant 3. If I start down here, I'm going to connect these points. It's going to come up, cross the x-axis, the y-axis, hit that max, come back down. There's another 0. And it just keeps on going. Super exciting. It does look like this tiny little sketch I showed when we were originally talking about the degree. So super exciting there. Still have some work to do. Let's jump to domain and range. Well, domain and range, there's no limitation to my graph. Again, since I knew it was a degree 3, even if I look down here at this initial sketch, I know it's going in both directions in terms of the x's, so negative infinity, positive infinity. In terms of the y's or my range, this is going to go down forever. This is going to go up forever. So again, negative infinity, positive infinity. Line of symmetry is saying, is there a mirror line? Is there somewhere you could draw a vertical line so that the left and the right exactly match? There is none in this case. And now we have to tackle the increasing, decreasing interval. This is, to me, one of the hardest things to look at. And what I'm going to do to clean this up a little bit for myself is I draw a number line. And a number line helps me break up my x-axis. So I'm going to draw this at a number line. And I'm going to focus on these changes of direction. So right here, that's a change in direction. That's a max. Down here, this was a change in direction. That was a min. And then it went on forever in both directions. So let's trace this graph a little bit. Here it is increasing. It stopped. Then it was decreasing. And then it was increasing. And it takes off to the sky. All right, let's do that again. Going from the left, it was increasing. So I'm actually going to write I and C here. And then my red, it was decreasing. I'm going to write DEC. And then in blue, it was increasing again. So I have an increasing. I'm going to change this to black so you can see this. So I have an increasing interval, a decreasing, and an increasing. Now, when you're doing that, you're always focusing on your x values. So if I'm looking at this stopping point, this max here, the x component of that max was 0.33. So the x component of the max right here was 0.33. When I look at the min, the x component of the min was 3. Now, I'm going to use those x values to write my increasing and decreasing intervals. Okay, so we said right here, this was increasing. So I'm going to write that as negative infinity, and it stopped at 0.33. Now, it doesn't do anything at 0.33. It's not increasing or decreasing, which means I'm going to make that a parenthesis. Now, it decreases after 0.33 until x is 3. So I'm going to write here, picking up from that 0.33, and it goes over to 3. Both of those, again, are parentheses because nothing's happening up here at the max. Nothing exactly is happening at the min. Then it's increasing again. So after your x is 3, you're in that ditch right there, it's going to increase one more time. So it's heading towards positive infinity. Now, I like to write it like that because together it should make up the whole number line. So if it stopped at 0.33, it's going to pick up at 0.33. It stopped at 3. For, again, that decreasing, it's going to pick up at 3. So these two together, if you were to smash it, should make up the whole number line.